introduced, I'm Carsten. I'm from Bar Ilan University, and my talk today is about secure multiparty computation. Why I'm actually interested in the subject, well, partially I'm doing research in this field. I'm in academia, working at Bar Ilan University as a postdoc. And I got into the subject, let's say, or I got the first time in touch with it 7 years ago when I first heard about this thing called homomorphic computation or homomorphic encryption. Maybe all of you have heard this, like fully homomorphic encryption. You know, you can encrypt your data, you can compute on it, and you know, it's all really, really cool and fun. And back then I was an exchange student in Switzerland, and I said, like I went to one of the lecturers, and I was in this lecture about FHE and this multi-party computation, and I said, you know, what's the difference? It's all the same. And once the whole lecture was over, I thought to myself, yeah, like you're never going to think about this again. It's completely uninteresting. 5 years later, I finished my PhD about secure multi-party computation, and here I am nowadays talking about it. So things can change. But for now, like maybe you've heard about it before, maybe you haven't. This talk is about what it actually is. It's going to be very informal, and it's supposed to introduce you to the field. It's not going to be, you know, you're not going to see any code. You're hopefully not going to see too many formulas, and so everyone can get something out of it. So first of all, what is multi-party computation? So imagine, as we have nowadays, or right now, the situation that, you know, you get sick. For example, you have the flu, you have a cold, you know, things escalate, it's a bit worse than you thought, right? So at some point, you may have to go to a hospital. So you go to the hospital, and yeah, so maybe some nurse carries you in there. And how does the whole procedure continue, right? Okay, they treat you, hopefully. In the end, you're going to be fine again, everything over, and they're going to send you a bill. That's the not so nice part about it, right? But lucky you've registered with insurance corporation or Maccabi or whatever in Israel. And then, I don't know, you forward the bill to them and tell them, guys, you know, pay the bill for me. You know, I give you money every month, so you know, you're my health insurance, please pay the hospital. So they send the hospital a message saying, was that your patient, and is this the right bill? And the hospital is going to say yes or no, right? And based on this, the insurance company is then going to pay money to the hospital. So far, so good. Nothing interesting happened, right? But now there's not just one patient. And in particular now, as we have the flu season, there's like lots and lots and lots and lots and lots of different patients. And let's say they all go to the same hospital, like just for simplicity, just for motivation, not for, just to motivate MPC. So okay, they all go to the same hospital, and then they all send their insurance, whatever bills to insurance corporation. And now insurance corporation every single time has to send a message to the hospital saying, you know, this was the bill, should I reimburse it? Yes, no, whatever. In the end, there's going to be lots of papers, there's lots of balagan, a lot of things are going to go wrong. And, you know, since we live in the 21st century and we shouldn't like send faxes or emails for every single bill around anymore, let's try something more smart, right? Let's say we do something like batch invoicing. Like we collect all the invoices, and then once a month we're going to go to the hospital and say, okay, I'm going to pay you. So the insurance is just going to go to the hospital and is going to say, did you treat any of my customers this month? From that, the hospital is going to say, yes, you owe us like so and so many shekels, dollars, whatever, and the hospital and the insurance company is going to pay the hospital. Sounds a lot smarter, right? It's if you have 100,000 patients, you don't have to send 100,000 things. You just do this thing once every month, and you're fine. Okay, so like still far away from reality, but just trying to do this, we may think some things could go wrong. The reason is that we need to find out who are the patients that they have in common. So let's say the hospital has a list. The hospital has a list of clients that they have, or they have a list of patients that they had in the past month. And the insurance company has a list of customers, right? And we kind of have to meet the two up, and match the two up. So there's a green list that's from the hospital. There's a blue list that's from the health insurance. So we kind of want to find out who's on both of these lists. Now the first thing that we could do is we just could send the, something is wrong with the mouse and everything. We could just send the green list over to the insurance corporation and say, you know, just find from my just find from my patients who is your customer, and then like give me the money for that, right? But a hospital is not allowed to release who it treated or like what they have been treating people for. Like that's private, that's sensitive medical data. And even in Israel, where everyone is like, you know, asking you about, you know, your job, your salary, your everything in a coffee shop or when you're just sitting at a bus stop, I think this is like, even in this country, this is something that you can't just release and like send to a health insurance, right? And the other way around, the insurance company can't, something is seriously wrong with this mouse and everything. The insurance company can't just send its customer list over to the hospital because this is private information of the health insurance, right? You don't want to send them like your whole list of customers and say, here you go, now do everything with it what you want, right? So you kind of have to match the two up. It's a problem that we call privacy. So this is where secure multi-party computation comes into play. So secure multi-party computation is a way of, you know, first of all, it means you send messages over a network. Like this bird is going to fly around and it's going to deliver messages between everyone, right? Everyone in the beginning had, I really don't know what's going on here. Let me, maybe that's better now. Anyways, in the beginning, everyone had some input to the computation. In the end, they all get some output of the computation. And the important thing about it is it's correct and it's private. Means that what you compute is actually, you know, what comes out is actually that what each party put into the computation. So their input values. This laptop is a mess. And at the same time, all they learn is the output of the computation. All they learn is this value y, even if someone is acting maliciously. Someone is like messing with the computation. Someone is doing something so everything goes wrong. So it's robust against tampering with the computation, and it at the same time only reveals the output and nothing else. And obviously for our setting of the hospital, this is kind of what we want to do. Because, like, let's say we have this magic MPC box, all we do is one hospital is going to input its list, and the medical insurance is going to input its list, and the MPC is just going to say, okay, I compute who is on both lists, and I'm going to output it to both of you guys, and there you go, everything is fine. So far understood? Motivation understood? Okay, cool. Everyone is nodding, I like that. So now, I want to explain how to build like a very simple MPC protocol. And all you need to do to know for this, what it is something called encryption, which I guess you are all familiar with, so here we go. First, we have to figure out how do we define what do we compute. Normally, you know, how you compute something is hardwired into these things there, right? This is when you open your cell phone, when you open your laptop, when you open your fridge nowadays, this is what you're going to find in there, right? This is hardware. Now, if we abstract away hardware, if you're an electrical engineer, for example, then you're very familiar with this. This is an abstraction of the green thing on the left side. But when you're a computer scientist, then you're much more familiar with this, which is an abstraction of the abstraction, and which is actually what you're going to work with. Now, if this doesn't make sense to you, no worries. It's just here for motivation. I'm going to explain to you more what this thing actually is. What you saw is something that we call a circuit, and the circuit is the programming model that you have. That's how you put the computation, like that's how you describe to the MPC box what you want to compute. And as I said, for the inputs, like parties have inputs, and let's say Alice has input x1 and Bob has input x2, and then like, you know, Bob has input xn. And now what they're going to do is they're going to feed these into what we call gates. You evaluate the gate function for each of these gates, and then you just propagate the values throughout this network, and out comes the output of the computation. That's how you would do something in Clear. You would have input values, you would apply like intermediate functions step by step by step. Out comes the output that you want to have. So that's how you describe a computation. And by the way, if you can do these two thingies, if you can do these two boxes that are called AND and XOR, you can essentially do all kinds of computations that you want. Like this is complete for everything you want to do. So yeah, that's all we care about. So we replace the big function with a lot of small functions. Now the only thing we have to do is how to implement these small functions. And this is where MPC comes into play. MPC is essentially taking the inputs, applying all these small thingies there, throwing out the outputs. There you go. And when you had, maybe when you were a computer science student, when you were having like technical computer science, then all you learned about is that these boxes are AND gates, OR gates, XOR gates, NAND gates, whatever. Like it's a very basic thing in computer science. I guess, yeah, if you studied it, you're probably familiar with it.
What does MPC stand for?
And MPC stands for multi-party computations. So multiple parties are doing this computation together, without revealing essentially what is not your input and without revealing what is happening inside here on these wires. That is gonna kept safe, gonna be secret. So now what I'm going to explain to you is the simplest way and the first way how this ever got into how someone ever realized this box, and that's by implementing one of these small boxes. So I'm going to explain to you how do you compute securely an AND. It's a very basic thing and it's a very basic tool. It's not the only way how you can do it, how I'm going to describe it to you. But I think it's a very simple technique, and I want to explain it because I think that you can get something out of it. And so let's start with how to insecurely do it. If Alice has a value and Bob has a value, and they securely want to compute this so-called AND gate, how could they do it in an insecure way? Like the dumbest thing that they could do is for Alice to make this truth table, right? Like these are both values that Alice could have. These are both values Bob could have. And these are all the values that can come out of it, right? 2 times 2, 4. These are all possible outputs. And Alice is going to have in the end 0 or 1, and Bob is going to have 0 or 1. And based on both of what they actually have, you just go into that box here in this truth table and you say, okay, this is the output. It's going to come out of that. Okay, the insecure way how to do it is for Alice just to make this table, to send it to Bob, to send her input to Bob, and Bob is going to take his input, just look at the box, and sends the correct output to Alice. So this is obviously correct. You're going to get the correct output out of it, but it's not private because Bob learns Alice's input. Right? We wanted to avoid this situation. So this is solving the problem by not doing it securely. But it gives you a feeling of what we might be able to do. So let's say we want to obfuscate this table. The first step, how we can do it, is to say, what is a 0 and what is a 1? Like, we needed this to define what the table is, but I can replace them with arbitrary strings. Right? If I'm going to write here, zero knowledge meetups are cool and zero knowledge meetups are not cool, right? And here's something else, it doesn't make a difference, right? This is just a table. It's a table of strings. So I can replace them, and for as long as I put like the right strings in here, like 3 times the same here, because here we have 3 times 0, and here one's a different string because this is a 1, then we're fine, right? If I can translate between 0, 1 and these things, and 0, 1 and these things, I'm okay. I can just replace numbers by strings. Alice can do that. This whole thing is still insecure because Alice is now going to send her input string which means which one of these two here Bob should use. But Bob can still retranslate it into her bit value. So, this is still insecure. Right? You see why it's like, but you understand what is going on, right? Nodding? Okay, good. Good. So, okay. So the next thing that I can do, or the next thing that Alice can do, is to say, well, now I'm going to encrypt what is going to be in there. Like, I see people laughing in the audience, like they probably have seen this before multiple times. So instead of putting a string in here, I can say I encrypt whatever is in here under this key and this key, right? And what is in here, I encrypt under this key and this key. Still not much has changed. Like, if Bob takes his key and gets Alice's key, he can decrypt the right value. Now the thing is, Alice is not going to send both of her keys anymore, but she's only going to send the key which corresponds to her input. Makes sense, right? Okay. But that means that Bob now can only decrypt, instead of 2 values, he can only decrypt, instead of 4, he can only decrypt 2 values. Right? It's still not secure. Why? Because, Bob can see if he decrypts this value here or this value here, and from this he can guess if Alice had a 0 or a 1, because, this thing here is the encryption, this thing is, it's supposed to be the 0 value, this thing here is supposed to be the 1 value, so Bob still knows what input Alice had. So what do you do in this situation? If you're a cryptographer, you think, okay, let's just flip them randomly, and there you go. And that's the construction. That's how you securely compute an AND. That's all you have to do. Alice computes these 4 encryptions. She flips them a bit around. Then she sends one decryption key to Bob, which corresponds to her input. But how's Bob going to find his own key for decryption? For that, cryptographers invented something called oblivious transfer. I'm not going to go into details what it is, but this actually gives Bob the right key. Let's say it's there. Explaining this might take a bit longer. But based on this, Bob can try to decrypt all 4 of these values. He's only going to succeed in one of them. And this one of them is going to give him the right output here, and that he can send back to Alice, and then they know what is the output of the computation. And intuitively, Bob doesn't know what Alice's bit was because, everything here is permuted. And Alice doesn't know what Bob's input was simply because, if she made everything correctly, then it's straightforward to see that. Now, yeah?
Yeah, actually I have a question.
Sure.
So it's an AND, so 0 and 1. So if the output is 1, they both know that they put 1.
Yep, sure, but in this setting, from the output you can already derive the input, right? Yeah. Because now you have an output of the computation which already gives you all the information about the inputs. The important thing is the 0. Because if Alice inputs a 0, she's not going to learn if Bob had a 0 or a 1. All she learns is that the output is 0, and it gives her absolutely no information about whatever Bob input was. Okay, more questions? Okay, so now there's multiple things that can go wrong with this, and this was originally invented in 1982 by someone called Andrew Yao, and people have been spending a lot of time thinking about, okay, Alice could make an incorrect table, how does Bob learn his input, how can you make this more efficient, and so on and so forth. So there's actually research going on even nowadays, how to do this for more than 2 parties, fair enough. But one thing I want to talk about here now is what happens if Bob aborts after learning the output. So again, to recap the protocol, because it was very simple, you send this garbled table, and Alice sends her key. Bob learns his key, and then Bob sends the correct output back to Alice. This way, both Alice and Bob learn the output of the computation, right? Now, malicious Bob could just say, nah. Right? Bob can just stop, not send the output to Alice. What are you going to do? In particular, what are you going to do if the service you're offering with your MPC to your customer actually requires that like both parties learn the output of the computation? Right? Maybe your application needs that. So you need to do something about it. So where there's problems, there should be solutions, right? But I have to disappoint you. This is something that in cryptography we call fairness. Because, you know, if only Bob learns the output but not Alice, it's obviously not fair. Right? Now the problem is that someone already more than 30 years ago, like mathematically showed if more than half of the parties are dishonest, then you can't get fairness. In particular, if you have two parties and one of them cheats, then you can't get fairness. Like the other one can sit there and wait for the rest of his life. He's not going to get the output of the computation. That sucks. Okay. So, and even worse, like all this MPC that people have been like developing in the past, like the 10 or so years, like actual protocols that you can implement, all of them have no fairness. And I already sometimes heard from like people who wanted to use MPC that this is like this for our application. This is just not making sense. Like if we don't have fairness, then you know our setting just breaks down. So the problem is, if you think about it, that like on a what is actually doing is that the adversary is incentivized to keep an important result for himself. So we want to de-incentivize the adversary to keep the output of the computation for himself. And I see the Enigma guys already smiling because this is kind of something that Enigma is doing. And now, you know, what happens nowadays if you have a problem that looks hard and that you don't know how to solve? Well, the first thing you can do is you throw blockchain on top. This is from a newspaper in the Netherlands. Like they now introduced the blockchain bus. It's like where you can pay with Bitcoin. In comparison to that, I'm now going to give you an application that is from cryptography, and where I think that blockchain may make a bit more sense than paying your bus ticket. Because for once, like when you enter the bus, it might be more expensive to take a ride than when you leave the bus, and like the bus ride might be shorter than the confirmation for. There's too many problems. Okay. Some researchers came up with this great idea of like penalizing someone for not giving the output. This is like, I would call it to have an insurance against cheating, and this can be implemented using a distributed ledger. For that to work, what you do is that every participant puts a deposit of some money on for example, towards a smart contract. And then, if someone cheats, that person that cheats or the participant that cheats will be identified afterwards, and his money that he put into the computation will not be given back to him, but distributed among the other ones who didn't cheat. And this way, you can make sure that if the output means something for you, but it only means money X, right? But you're going to lose money 5X if you withhold it. Then you don't have a monetary incentive to actually do this. Okay, that's a way around this impossibility result, and that's why I find this as a theoretician interesting, because getting around impossibility results is kind of what we do all the time. First of all, we prove that something doesn't work. Second, we prove how to actually make it work by tweaking a bit with here and there. I guess everyone here is familiar with what a distributed ledger does, right? So I'm not gonna talk about that now, and that's gonna be a lot of slides. So let's only talk about what is multi-party computation, where you punish abort or where you punish cheating. How can you do this in the presence of a distributed ledger and a smart contract? So first of all, the parties have their inputs again, and they also each of them has some money. So now in the first step, fancy animations, Alice, Bob, and Charlie are going to send their money, let's say, towards this, I'm not a blockchain person, but I'm going to say they send the money towards the smart contract. So the smart contract will later on be able to decide what to do with the money if necessary. Next, they run the secure computation the same as before. But in addition to giving them giving them some output, they're also going to get some kind of proof. They're going to get like a testimony that says, you behaved correctly during the computation. And now, each of them can send this proof to the smart contract, and the smart contract is going to look at the proof, and it's going to look at the money that each of them gave. And if these proofs, if they are not forgeable, if they are zero-knowledge proofs, which are sound, right? They, first of all, do not reveal any information about the inputs of the party, so privacy is still fine. And since you can't forge them, at the same time, this gives you some reasonable information if they cheated or not. And the smart contract is just going to look at these things and is going to redistribute the money based on who's been naughty and who's been not. Make sense? Okay, great. So this was invented, or this was first presented in 2014. And if you actually want to work with MPC, or if you want to learn a bit more about this, and this is what this talk is about, I'm just going to provide you with a few references, with a few pointers. The slides are going to be online, so you don't have to like write them down now or take pictures, but if you take pictures if you want to. So first of all, there's a great GitHub repository by someone called Dragos Rotaru. It's called Awesome MPC. And it gives you an awesome list of all the information you want or maybe don't want to have about multi-party computation. If instead you think, okay, Carsten, from your talk, I kind of got what MPC is doing. I want to play with it, right? I have some idea. I want to have a prototype. I want to design a prototype. Okay, here are two references. One of them is an MPC library from my research group. And because I'm from Bar Ilan, I kind of have to say that this thing is there. And no, but it's good. Like, download it, check it out, no problem. It's solid work, and we actually have like a real programming team that implemented that. So it's not only like academic, master students fiddling something together and make it run. And then there's something called Scale Mamba, which is by the research group at KU Leuven from Belgium. And they have a different programming model. They have different security assumptions, but that's also something where if you have an idea for what you want to develop, download one of the two or one of the other libraries which gives you that and play around with it. So there's code there to implement your MPC application. You can do it. If you decide, like me, that you kind of want to learn a bit more about MPC, I want to refer you to a book, which you probably also can find online, about secure multi-party computation. It's also about secret sharing, but ignore that part. Like, I don't understand it. It's written by someone who is a crazy mathematician, and I have a hard time following him, his writing style, but he's a good researcher. And in terms of fairness for secure computation, there's been some, like just as a reference, this thing about punishable abort, as I said before, other people have been working on this. There's been some recent work of myself and two other researchers from IOHK, where we try to give like a detailed construction for this multi-party computation on the blockchain, and where we give like a mathematical solid proof, and we hope that it's like as efficient as possibly can be. And if you feel like you want to implement it, like go there, look at it, and if you don't understand it, write me an email. And yeah, so much from my side. So if you have any questions, feel free to ask. Sorry, just a question.
Hi. My question is
microphone is not on.
Time. Okay, it's okay. My question is, where is the boundary between what you called fairness and like could you repeat again the concept of fairness and what are the limitations of it?
Like fairness means if the bad guy gets the info, then the good guys get the info. That's the definition of fairness. Like, bad guy gets output, good guy gets output. And what Cleave showed in 1986 was there exist functions. One of them is the XOR function, which is like one of the most basic things that you can have, such that if you have So if you have a third of the parties being corrupted or half of the parties but you have a broadcast channel, then you can't compute this function with fairness. So there are functions you can compute fairly, and there's a whole different area of research. But in general, many interesting functions that you want to do, you can't compute with fairness if half of the parties are corrupted. Now there are lots of ways how to get around this, and one of these is using a blockchain. There are other things in research, like just Google fair computation, and you're gonna find lots and lots and lots of different pointers into this area. There was some question here.
So it.
I can hear it.
Okay, so for developing MPC, it's platform independent, right? So on whichever code I'm writing for smart contracts, I can just, it's an ideology almost. So you can include it on any platform. Or is it dependent?
Like, what kind of platform you mean?
So when I'm coding in Solidity for a smart contract, it's just like I would have this feature of several people being able to have an input, do the computation, have the distribution, right? It's just like that. Okay. Is there anything else?
So most of this work is independent of what kind of distributed ledger you use. What you need are several features. Like that's the engineering side, and it's specified which features you use. In our case, we wrote down like you need this and this and this and this and this feature that the distributed ledger is giving you, something like a smart contract, and that you can broadcast something, which, you know, and then in the end, this allows you to implement it. If you want to code your MPC in C or Java and run it on your smartphone, and if you want to implement a smart contract for Ethereum or whatever, in whatever like programming language you want to have, that's design decision. That's like this stuff works independently of the specific distributed ledger you use as foundation. Okay, I guess I'm running out of time.
No, it's good. Just a question, follow-up question.
Okay.
So I want a follow-up question about the platform itself is what kind of cryptographic primitive do you need to have efficient zero MPC on, for instance, the blockchain? Like what do you need to verify the fairness of it?
So what we design is a specific protocol for, we use a specific MPC protocol and we tweak it for blockchain. All we need is signatures, hash functions, and a bit of oblivious transfer, like that which you can do if you have like certain kind of encryption, and then we write how to put everything together so it works. That's all you need. Like you don't need homomorphic encryption. You don't. Okay, you do, but you don't need inefficient homomorphic encryption. You don't need pairings. You don't like you use only very simple things which have been developed 20, 30 years ago, and you can, if you put them together in a clever way, then magic. I think you were first.
So you mentioned circuits. So circuits composed out of many logical gates. So does the observer see intermediate results between the logic gates? And no. So the other question is, the only 16 possible functions which takes 2 bits as an input. Does it create a problem or not?
So the point is that you can represent any kind of computation by decomposing it into these small, like into functions that have 2 inputs and 1 output, and actually this is not gonna lead to any problems. You had a question, and you had a question. I think you were first.
So from an architecture standpoint, you have the basic hardware, and then you have the TCP/IP and the TLS encryption on top, and then you have the consensus layer, and then on top of that you have the application layer. So where does MPC fit in? Like, what layers is it interacting with, and how can you talk a little more about the infrastructure and plumbing aspect of it into the blockchain architecture? So
MPC itself is independent of blockchain architecture. MPC itself, as maybe I wasn't like very like precise about this, but the whole MPC essentially runs independently of the whole blockchain infrastructure. you'll just need to be able to send a message to the blockchain, and you need to let a smart contract run and essentially call functions, have a function, have an API ready which you can call, which does that for you. But most of it runs completely independently of whichever distributed ledger